Hello. So before I get started, I want to ask quickly, how many here actually ever programmed in Rust? That's not a lot of people, so maybe there's something to learn here. My name is Armin Ronacher. I built Python software for a very long time at this point. And I started working a little bit with so I originally worked on a lot of libraries like Flask and other things, and then about 2 years ago I started working on a software project called Sentry, which is a software as a service, a crash reporting service. And one of the nice things about this is it gives you the opportunity to optimize like processes that we have to do. And I started playing around with Rust in this context a little bit, and so this is my experience report about how we did Rust at Sentry and how maybe you can utilize Rust in your own projects. If you want to find me on the internet, these are some of the locations that you can do so. I, as mentioned, built this thing, now work at Sentry. And a lot of people have talked to me recently over the last couple of years. Whenever they talk to me in person, I heard that you're doing Rust now, do you still do Python? And the answer is that yes, I still do Python. In fact, I love Python, Sentry loves Python, and there are a lot of reasons for loving Python that didn't change over the last couple of years. The biggest one is that the ecosystem is really strong. And this is something that, for instance, if you compare it to Rust, the Rust ecosystem is very specific. In some areas, it's very good. They happen to overlap a little bit with the work that we're doing, but it's different. The ecosystem is very hard to get rid of. So, for instance, if you need mathematical plotting libraries like matplotlib or statistic libraries, there is a lot of stuff already there that's really good to use. A lot of this is already written in C, for instance, behind the scenes, so you actually get performance out of this as well. So there's no reason for dropping that, because one of the arguments for actually using Rust is performance. So we use Rust to augment Python. We don't use it to replace it. It's particularly true because Python is very good at fast iteration, something that Rust is not good at. The compile times in Rust are not particularly great, and it's a compiled language, so iteration speeds are not nearly as close as you have as Python. And this is, I think, the biggest redeeming quality of Python compared to many of the other systems that we're using, is that the ecosystem is very stable. There's very little breakage that comes with package updates. It's very rare that deployments fail because of something. There's one famous case that was recently where I think setup tools got an update that broke, but it's very rare. In comparison, for instance, to our front-end JavaScript applications, where stuff moves so quickly that sometimes it just doesn't work. For us, also one of the good features in Python is that it has very powerful metaprogramming, which makes it very possible for us to build APIs that are really nice to build internally. We can instrument a lot of the code so that we can see what it's doing at runtime. And we have fast interpreter introspection, which means that we can actually see variables when a crash happens. We can look at the threads that are running. So it's for building software as a service applications is really great. And this doesn't at all apply to Rust. So all of the Rust code that we have runs very efficiently in a little box. But when it breaks, we have no way to introspect this. And we don't have a lot of metaprogramming capabilities in Rust either. So they're very different, and one would not replace the other. But the arguments for Rust are speed. That for us is a big one. And the second argument for us is that Rust has a lot of functionality which we don't find in Python. So in particular, we at Sentry need to deal with crashes that are coming in from users' applications. And those crashes involve, in some cases, dealing with raw binary data. And Rust is actually really good at this, because Rust is at least partially written in Rust. And since it's a compiled language, it has bindings to LLVM. It has there are lots of people that wrote libraries for parsing Maho files, which are OS10 binaries. So there's a lot of functionality which we can use in Rust that would also exist in C++, which doesn't exist in Python. So by us bridging this, works really well. Reliability is also, for Rust, it's a good argument for us. The code that we write in Rust doesn't really break. It's strongly typed, it's very easy to test, and then once it runs, it kind of keeps running. So what we use it for is I don't know if you ever heard of dwarf files, but it's a debug format, and there are libraries for Rust that can parse this format. And the only other libraries I know that do this are written in C and C++. And it's a lot more fun to work in Rust than in C and C++. So that was a big argument for picking this. Mach-O is the binary format for Mac binaries and iOS binaries, so there's also really good support for this. We also parse JavaScript source maps. That was the first thing we did with it. It's huge JSON dumps. And actually turned out that that was, from a performance perspective, doing that in Python earlier was not a good idea. Recently, we started doing ProGuide files, which also like huge text files that need to be parsed. And then we've built a command line utility in it. The first 3 of those things are actually written as Python modules. So there's a Rust library that then is available from the Python interpreter, whereas the command line tools is a full Rust application that has no Python in it. So if you use Python, then it makes a lot of sense to see like how is Python compared to Rust as far as the basic sort of tooling goes. In Python, we have a lot of tools that we have to work with. I think the majority of us are probably using virtualenv, pip, distutils, and setup tools. And in Rust, that comes out of the box in form of 2 utilities, one of them called rustup. Rustup is a way for you to manage multiple Rust installations. So instead of installing Rust, you install rustup, and then rustup manages your Rust installations. So for instance, you can track stable or beta releases at the same time, and you can switch on a project-by-project basis between them. The nice thing about rustup is also that unlike most other like multiple Python or Ruby managers, it also comes with a full documentation. So if you have rustup on your machine, you can run rustup doc, and it will open the documentation for the version of Rust that you actually have in the browser. So it's even if you don't have internet, it's pretty good for this. Cargo is a second tool. It replaces pip. Cargo can install dependencies for your Rust project, and it can also build the Rust project. So if you have a project, you don't ever have to interface with the Rust compiler. You can do it directly through Cargo. So it functions very much like a combination of pip and virtualenv. The second set of tools that is quite useful for this is called rustdoc. And rustdoc can build documentation out of your Rust projects. So if you have a library or an executable, and there's functions and structs and all kinds of other stuff in there, you can just run a cargo doc, and it will build the documentation for it with the help of rustdoc. And it opens up in the browser, and you can read it. It's a little bit like PyDoc. It's less like Sphinx. So it will build documentation that looks a little bit like every object in your API, and then the documentation string for it. But it's very convenient that it's built in, and it also means that if you have dependencies in your application, if you do cargo doc, it will also build the documentation for all of your dependencies, which means that you don't have to go to the internet to consult the documentation. It's always there. And it is the documentation in correct version, which is really good. So yeah, this is rustdoc, the documentation builder. So I have a lot of code on those slides, and I think for the most part, you can kind of ignore it. It's just sort of a way, as a taste to see how the language looks like. So this is the obvious one. I hope it's big enough. It's hello world. It's a function called main prints hello world. But it already shows one thing, which I think is interesting for Rust. There is an exclamation mark after sort of the function name. It's not a function, it's a macro. So it expands at compile time into more complex function calls. The reason it's doing that is because you can pass variables in there in a way, and then these variables will be type checked individually. So if you would print, for instance, hello world, but the world would be a second argument, it would make sure that the format string matches the variable. So it very efficiently generates the correct code, and it type checks it. And the reason I'm mentioning this is because macros are actually very powerful, and you can build them your own. You can also write compiler plugins for the language. So a lot of the more involved libraries for Rust will have some of this meta-programming code in it. This is a second slide I want to show, which is It should show two things, and I don't know how well it will do that, but the first part is there is it will show you a little bit how import syntax looks like. It's more or less similar to how you do it in Python. You have modules, you can import stuff from it. But there are two differences. The first one is, in line 2, you can see there's a hash map being imported. And it's a type, and it's a type that's generic over the stuff that's in the hash map. So it's like a dictionary. But unlike a Python dictionary, which can store arbitrary objects, this hash map, when created, will be restricted to certain sets of types. And the biggest restriction you will see here is that we are actually reading strings from the standard input. And these strings, because they're red here in sort of this in the middle of the screen, they will be stored in the hash map as a string. So the hash map will, from that moment, be restricted to strings only. And the reason why you don't ever see that this is a hash map of type string is because Rust will actually infer the types for you. So you don't have to write this a hash map of string to string, string to integer, because we're counting up. It's a hash map that will automatically get this type information. And the second thing I want to point out is that there's an import up there for a thing called buff read. But if you actually look through the slides, through the code, there is no buff read anywhere here. And what this does is it's a trait. And traits are a little bit like in Python, these special underscore methods. So for instance, if you want to add a plus b, in Python it will be a add b. Traits are similar to this. So traits are ways to add special behavior to objects, even if the objects are not yours. So for instance, buff read is the behavior for all the methods for doing buffered reading on something. So when I create a buff reader here in the middle of the screen, the lines method will magically appear just because buff read is in context. So I can add methods onto other things this way. The interesting thing about Rust is that it tracks ownership. So if you, for instance, here change, I don't know if you see this, this used to be a conversion of items into an iterator, and then it only takes the first 10 items. If I change it to counts, which is an object from up there, it will actually not compile. And the reason for that is that it will tell you that this object has been moved into something else. So Rust follows a very strict ownership idea that any object can only have one owner, and that owner can borrow it out to some limited degree. But it will stop you at compile time from doing all kinds of stuff that would be perfectly fine in another programming language. So that's how this looks like for the most part. But I want to show you that Rust is actually very close to Python in many ways. It follows the descent of Python. I think it's a beautiful language. And one of the ways in which it's beautiful in my mind is that it has a lot of support in the language for effectively automatically doing things that are very boring. So for instance, if you have written a web API in Python or you consume the web API, a lot of the things that you will do is manually parse some JSON stuff, drag it in, drag it out. With Rust, you have this automatic ability to derive things. For instance, by saying this derive me a serializer, it will automatically make this struct into something that can serialize into JSON. And I don't have to do that. And then this is from actually more or less copy-pasted from one of our tools. This does an HTTP request and then automatically converts it into a list of deployments. So it's like the entirety of serializing, deserializing is completely hidden for you. It follows Python's general rules of being explicit rather than implicit. Biggest one is there is no none in the language. So everything has to be explicitly set as optional. Then it generally, I think, follows the idea that simplicity is better than complexity. I want to just generally show you that this looks more or less like Python code. I mean, obviously it's different, but it definitely doesn't look like C code or C++ code, even though it's at this very low level. And this is an example from Redis library, where you can do very complex operations with it, and it doesn't really look very complex. It's just nested, not nested calls, it's chained calls. And this, I think, is the best part of the language. It gives you a lot of information about what you're doing wrong through linters and warnings and compiler errors. So for instance, here I'm opening a file, but I'm never handling the error that's being returned from it. In C, that would be like not a warning at all, because it wouldn't even know if you have to do something with return value. In Rust, you can explicitly define what should happen. So just side by side a little bit, special methods in Python. will become traits in Rust, so they are individual, you can make more of them, you can implement them for any object, you can take other objects and add your personal traits to it. Errors are very different, and I think that's the part that's really relevant. If you want to use Rust with Python, very often you want to build extension modules, and errors, you have to make sure that they are being caught within Rust and then translated over to the Python world in some way. There are two mechanisms for errors in Rust. One of them is called panics, kind of like exceptions, and the second one is explicitly returning results, and that's basically like returning a special value that indicates failure. That's, I think, an interesting part that as a Rust program we have very quickly seen, but it's a concept that doesn't really exist in Python as much. If you raise an exception in Python, it bubbles up to whoever decides to call it down, catch it down. So very often you use, for instance, a library like, let's take a request for an example, and make an HTTP request. Instead of getting a requests exception, you might get a socket IO error. And the reason for that is that nothing in requests catches down the IO error and converts into something else. So you can have these errors bubble up, and there might be errors in it which you don't really expect from the API. In Rust, you can't do that. When you propagate an error, you have to convert the error into a common type, or you have to handle it internally. So there's an idiom in Rust called the question mark operator, which will try to execute an operation, and when it fails, will convert the error into the common error of your library. So a user of your code only sees one error type, and that might have sub-error types. So if you want to try it, the way to do it, I would recommend, is to build extension modules. And I had this argument with a bunch of people that said, like, the future is service-oriented architecture, and you should build like individual Rust services, individual Go services, and this would speak network calls to each other. That's a lot of complexity, and I don't actually think it's a good idea. And there is definitely more to the world than a monolithic application and service-oriented architecture. I think it's absurd. The solution for this is modular code, have individual bits and pieces that can be individually deployed, and then just live in the same interpreter. So extension modules is a very good way. So how do you marry Python and Rust? And this is the part where I find a little bit of frustration in it, because I think I found a really good way in which it could theoretically work, but in practice, it involves a lot of pain and sweat and tears because of setup tools. And I don't know if you ever used setup tools like internally, tried to make it work in ways in which it was not originally intended to be used. So the way I would recommend, or the way I would like it to work, and I can give you an indication of how good it actually works at this point, is you build Rust library, you make a C ABI for it, which is more or less means the Rust library can be consumed through CFFI or C types if you want, and then you import it in Python. The tools for this is Cargo, CFFI setup tools, and the wheel thing. And this is sort of what I want to achieve. It's not to use libpython, because I will skip ahead a little bit because I want to show you this part here. It's terrible. This here. If you ever went to the pip page of Pillow, it's a library written in C. It edits images. Whenever these people make a new release, they're heroes, because just for Python 2 and Python 3, not counting, I think Windows is not on there, so just OS 10 plus Linux requires a total of 21 builds, which means they have to make 21 individual releases for one release because of the binary dependencies. And the only reason for that is because they link against libpython. So my goal is not to link against libpython. And that is currently really hard. So that would require, and we achieved that at Sentry, but the tooling is very, very custom, and I would like to actually raise awareness a little bit that this is something that would be nice to build, because it would also help people that use C and C++. So the path to success is not to link to libpython, but use CFFI. Because then, this is what we do. You end up with just the package name in the wheel format, just the version. It works with Python 2 and Python 3. It doesn't link against libpython, so there's no ABI. And the only thing you have to do is add the platform tag. And theoretically, you can get away with 3 builds, ignoring Windows. Windows would be 4 builds. And you can do this. So there's a catch to this, and this is where it's absolutely absurd. You need to basically build a version of your library, if you want to have it running on Linux, with a very, very, very old version of Linux. So you can install these Docker images. It's called many-linux 1. I don't have anyone ever built binary wheels for Linux? No. So the way it works is these Docker images, if you install them in your Docker, they're very old. They have an ancient version of CentOS in it. And I think, so it's definitely not supported anymore. I think at this point it's 8 years old. It doesn't do it basically can't do any SSL requests to any modern server because it doesn't support SNI. And it is really super painful. There are some modern tools in it, but more or less not really. So for instance, there's an ancient version of the GNU compiler collection in there and all kinds of stuff. And this is sort of the blessed way to build binary extensions for Python. And it's a super manual process. So this is sort of my point to raise awareness is it would be really cool if people that have an interest in either Rust extensions or C++ or C and that feel a pain in maintaining this to bundle together and then work on a way to actually bridge between Python and Rust or between Python and C++ that doesn't require libpython. So I want to quickly show you roughly how this looks like. The bridge between Rust and Python is you have an error handler. This error handler is more or less set up that when you actually raise a panic, an exception in Rust, nothing happens. Then you need to make a function that you execute which will indicate an error to the Python library. So when you fail in Rust, the Python side can know that if an error happened. Could look more or less like this. So you have an error that you indicate on that an error happened, and then in Python you look at this. Then you do all kinds of magic to actually set up a common way to catch this down. You don't have to look at the code. I just want to point out this is actually a lot of tooling that goes on before you have one function. Then you need to actually build a reusable thing that sets up the landing pad, and only then you can actually define one function. And we are doing this right now manually all the time. Then we have to actually bridge this through a library header in C, because the common interface between Rust and Python sadly is C. Then we can finally call this. And it's a lot of work. I did this for 3 or 4 libraries at this point. It's kind of frustrating, but the problem is like a lot of reusable tooling doesn't exist. So what is missing? We need a better way to build wheels, reusable Docker images, and Rust FFI. So a way to not go through the C layer, ideally. But what are the results? And I think this is the part where I want to, despite the pain that you might see in this, the results are pretty good. So this is total CPU usage for all of our servers before the deployment where we introduced source map handling in Rust and the part after. We not only basically killed the entire, the servers basically were idle at this point. We could throw a bunch of servers away that we didn't have to pay anymore for. So it obviously was saving money and it was saving CPU time and it just made it better. But it also made us realize that we don't have to ditch the entire Python runtime. We only have to put individual problems into faster solutions. So for instance, source map handling for us was 30% of what we did in total. By just putting this little piece of code into Rust gave us a lot of room that we can use the Python runtime effectively in other ways. The problem is when things goes wrong. This is a bug I introduced 2 days ago. After deployment, all the servers ran out of memory. Reason for that was that there was a bug not in the Python code, there was not a bug in the Rust code. There was a bug in the shim between them that caused the destructors never to run. So memory was just never freed. So I think it's great, but we need better tooling. And if anyone has an interest in Rust as a language or in C++ as a language that we want to use with Python, maybe talk to me afterwards, because I did this so many times now that I really want to actually build a reusable thing so that instead of this becoming like a talk about all the complexities involved in it, it becomes more of a, hey, there's this one thing you install and it's awesome, you write a Rust function and it becomes callable in Python. Because I actually think that as a language, it's one of the most innovative things that happened in the last couple of years, and the fact that we can use it in Python is really valuable. And I think it would be great if this sort of mindset starts to develop a little bit, that you can actually combine Python with Rust for very good effect. And with that, I take questions if anyone has any, or suggestions about how to improve our setup.
Thank you. Right, so the questions are, is Rust inspired by Swift or Swift inspired by Rust?
It's both. So Rust is, the joke kind of goes that the current version of Rust is built in the previous version of Rust, is built in the previous version of Rust, and they go all the way down until there was a version of the language which looked completely different 10 years ago, or 8 years, I don't know when it actually started. So what has happened over, I would say, the last 4 years is that there are a lot of people that actually involved the Rust language, got ideas from Swift, and a lot of people that work on Swift happen to also be Rust developers. So there's a lot of intermingling going on. So Apple got a bunch of engineers that used to work at Mozilla, at least temporarily, and there's a lot of information exchange going on. They have a lot of very similar ideas, and there's even talk going on about one of Rust's biggest features, which is the memory tracking model, to maybe make its way over to Swift as well.
Thank you. Who uses Rust and how big is the community?
So I think there are a lot of Rust users at this point that are very hidden from the world. So for instance, a lot of backend services start to look into Rust as a way to solve individual problems like we did. I know that Dropbox is doing that. I know that obviously we're doing that. But there are, I don't have a list right now, but if you go to Rustlang Friends of Rust, there is sort of an enumeration of companies that are using it. Another way I see people using it is, for instance, the company that built Habitat. I think, is it Habitat? Yeah, I think it's Habitat. I think it comes from Opscode or Chef. They built their new deployment system entirely in Rust because one of the biggest problems with distributing command line tools is that you not only need a command line tool, you need a runtime for it. You need to have the right version of Ruby or Python or whatever. If you actually ship a Rust binary to users, they don't have to have anything other than that binary. And how big is the community? It's very hard to say. It's definitely one of these small languages at this point. It's not like Go that's exploding very rapidly and becoming like everybody wants to build the services in Go, because Rust is really only good for a subset of problems. I think it's very good for high-performance code. It's very good for consuming REST APIs, surprisingly enough, building command line utilities, building extension modules, but it's a horrible choice if you want to build everything in it. So people don't build entire applications in Rust. They build little bits and pieces. So it's very hard to look over the entirety of the community. One of the things that's great, though, is that the community is an actual community, so you can get involved in it. They organize conferences. They have an outreach program. There's a lot going on. So it feels very welcoming to actually participate in it, even though it's such a low-level language, unlike C++, for instance.
Thanks. Do you have a Git repo or read the docs that we can read and learn what you did?
Yeah, so I will put the slides on my website, and I will link to the stuff, how we are bridging Rust right now. So the reason why I want to quickly point this out, because when I did the slides originally, they were a lot more positive, because I didn't realize that we had a massive issue in how we actually build the binary wheels. And I discovered that actually the way we're doing it happens to work by accident to some degree. So I want to point out that maybe not go entirely by our code as of right now, because I want to fix it by next week. But I want to put up a repository that actually shows how you can build an extension module for Python with Rust that you can actually start looking at. Maybe together people could help to actually make it into a reusable thing. And I probably will write an article about this at one point, how we actually do this. There's one in the Sentry blog. It's a little bit outdated now.
Thanks. And are you staying for tomorrow's sprints?
Sadly not, no.
And I think that's all the time we have. So thank you, Armin.
I want to, can I quickly answer the last one, the Python one?
Okay, sure.
It links against libpython, same problem. If you want to build reusable thing, 21 builds or more. So that's one of the reasons why we didn't do it.
Right. So thank you.